Great. I'm going to ask that all the panelists will turn on, go ahead and unmute. And if you feel comfortable, go ahead and turn on your screens. We'll start the panel roundtable. So some of the questions that came in are directed to each of the three panelists, and I'll field those. And some of them were quite general that we'll discuss. So I'll start off with a technical question for Alexis. Are you still with us?
Yeah.
All right. So there was a couple of questions that came in about the fixed CD4 cells that you had. So when you're looking at the stain index initially, were the fresh and fixed, were the fixed done, or was the staining done prior to fixation, or was the staining done after fixation?
It was done after fixation. I mean, I call the cells fixed because this is immunotrol, so it's essentially a reagent.
Right.
I don't do any other fixation except using Optilize C, which adds a little bit of fixation, but it's not too much. So essentially, the samples are fixed by design. Yeah.
So thinking about this, and I think this is really useful for all of us here, along those lines, since it was fixed afterwards, has anybody, to your knowledge, tested different fixatives to see how that affects the different fluorochromes? And when thinking about the spectral cytometers, does it change the spectrums?
Look, I talked to Temo Fisher in Australia about that. As soon as I saw this, my first concern was COVID patient. All the human samples need to be fixed, and fixation could be for PFA for 30 minutes and boiling water. I don't know. So the fixation could have a great impact in your panels. And I wonder if there is any fixation that is not producing autofluorescent. That would be awesome. If there is something that can fix cells without creating the autofluorescent background that you get. I don't know if you guys know about this.
I don't know. Are Jolene and Elise, are you guys working on such a fixation protocol that you can tell the rest of the audience?
Not that we could talk about, but it's really great to hear what the problems are, and so we can start looking for solutions. As we enter this spectral world, there are some things that are different, and while the autofluorescence is a great tool to have, it also presents us with some challenges. So I appreciate knowing what your wish list is.
I'll second that.
Yeah, and that leads to some other questions, right? So when we're designing these large panels and thinking about like whole blood or other tissues where you have a heterogeneous population, that each of the cell subpopulations have different autofluorescent levels. How can you deal with that? And when you're thinking about autofluorescence extraction or subtraction, what are your thoughts on this?
To me?
Yeah.
So, that is a big problem. When I started getting involved into panel design for the Aurora, I never actually thought of autofluorescent as a factor. But then when I found this sample from one of our colleagues, that he was trying to find a tomato reporter, essentially imagine this kind of project. You have a gene reporter, tag whatever, it's a tomato fluorescent protein, and you want to know in all the subsets in which tomato is expressed. Now tomato looks like an amazing fluorescent protein. It's the brightest fluorescent protein you have. And the tomato region might look like it's not like a more critical autofluorescent region you can have in leukocytes, which is typical in the UV and the violet region. But still, you have things like alveolar macrophages that are insanely autofluorescent all over the place. So we didn't have any previsions for that. And the funny thing is that when my colleague started analyzing the samples in the Aurora and the Forteza, his conclusion was it doesn't work. So there's a simple idea of having a high autofluorescence sample means that he will not see the signal whatsoever, even when alveolar macrophages are the ones that express the most tomato. So it's something like 70% of expression, yeah? But you only see that expression when you use autofluorescent extraction. So one thing that I will do is to try to find regions of low autofluorescent, which typically will be, if you want to target, if you want to market something, if you want to detect something with a fluorescent antibody, I would go for, imagine APC's Fire 750 or something, you know, one of these super infrared kind of fluorochromes that typically you don't find much autofluorescent there. There are several pockets, like Brilliant UV 661 seems to be in a good pocket as well. So you will have to actually look at your samples. You will need to kind of know the autofluorescence of the subsets that you have, and you try to find the regions that are quieter to keep those regions for the rare markers that you want, that are critical for your study. That essentially means taking autofluorescence into account when you do panel design, which is something that we don't do. Sometimes we don't know what the autofluorescence will be. So it might mean essentially tweaking the panel once you realize that autofluorescence is actually a factor. Yeah, essentially it would be that. Typically you don't know. I mean, if you know the population, you can tweak around. Look, sometimes people know this. Like how many times people will tell you this antibody worked for these subsets and this marker, but not the other one. And the reason why the other one is sitting in a region of high autofluorescence. And people have seen the resolution better with this marker somehow. So people might know this, people that are experienced in analyzing some cells, but when you're dealing with things that are really complicated, like tumor cells or, you know, muscle cells and cells that are the typical lymphocytes, I think you better know the autofluorescence before you define the panel, or tweak the panel after knowing the autofluorescence. And try autofluorescent extraction, but that will be my last resource. You know, I will try not to get there if I can avoid it.
That's really good. So along those lines, something that we've done, and I think maybe get your thoughts on this. Thinking of autofluorescence, it doesn't necessarily have to be done on a spectral analyzer, right? So you can, thinking about all cytometers are essentially spectral cytometers, right? Just not full spectrum.
Okay.
Right.
Yeah,
so
you can. Okay.
One of the things we've done is taking different cell types like mast cells or alveolar macrophages and even T cells and run them as unstained cells on conventional cytometers. You know, pick your favorite cytometer and you get the peaks and valleys of where the autofluorescence is. And you can pick those valleys, as you were saying, for those markers. And in the case of a mast cell where it's so stinking bright, you know, we can pick those valleys where we have maybe more sensitivity or we want to check those, because on a mast cell, you're really limited on a conventional cytometer, right?
Something that you should do is that you can do, because that's something that I have seen in the Aurora. Lymphocytes have autofluorescence, yes, but it's not as strong as to compromise your measurement. Normal lymphocytes, I'm not talking about, you know, like leukemia cells or, you know, typical lymphocytes, they don't give you any autofluorescent extraction benefit. So if you were able to run, imagine the samples in your instrument, in any instrument, and you compare at any given kind of detector settings, that you want to choose, you do a relative comparison, lymphocyte to mastocytes, alveolar macrophages, monocytes, you will know which populations are actually very autofluorescent by essentially measuring intensity relative to lymphocytes. Yeah. That's something that I would do, for instance, if I'm doing things in the Aurora. I would not bother to mix or extract autofluorescence of anything that is at the level of lymphocyte. What you say about using conventional instruments, there are several things that are limiting when you talk about conventional instruments trying to do autofluorescent extraction. The first thing is that typically you are already limited by the number of detectors that you have. So when you're thinking of a panel, imagine, to maximize all the detectors that you can use. And when you're talking about autofluorescent extraction, you might need to have some empty channels that will help you to capture autofluorescence anyway. You might even go in your panel design with markers that will override or fall on top of the autofluorescent region, where you might want to have autofluorescent detectors to be by themselves. To give some kind of, imagine autofluorescent as a photogram, you want to have them some space so you can resolve them spectrally after that. The other thing is that one of the things that I have seen with spectral instruments and the Aurora specifically, because I initially have a 4 laser instrument, and then I changed to the 5 laser instrument. Now, something really funny that happened in the transition from 4 laser to 5 lasers is that dyes that are emerging from violet to red, yeah? Violet to red dyes that you can run in the 4 laser instrument, when you run them in the 5 laser instrument, reduces spreading even more, yeah? So the quality of your panels are better in an instrument with a UV excitation, even if you're only dealing with violet to red dyes.
Which laser did you add? What
the
4
UV,
laser
the
did you
UV,
select?
the UV, the UV.
Okay.
So it was initially a violet to red, and then it was the UV to red. And I run panels that were violet colors before and after, and the panels and the spreading reduces by adding the extra 16 colors in the UV. So the spectra is not only good because of the spectra, it's also good because of the number of detectors that you have. So it gives you a fine distinction of the fluorochromes and also of autofluorescent, and allows you to extract autofluorescent without leading to a lot of error. Yeah, because autofluorescent will be clashing with all dyes. The same way you do panel design and try to avoid dyes to be spectrally overlapping, so you don't have spreading at the end, autofluorescent will behave the same. And since you most likely will realize autofluorescent after you have done the panel and you're looking at your samples, you know, having a spectral instrument with 64 detectors allows you to still have maybe some chances to remove the autofluorescent without compromising the panel as a whole. Yeah. But look, something that I would love to do, because you can treat typical instruments like spectra, you can do that with FCS Express. And I'm sure maybe the new compensation tool that Flojo have might be also essentially treating conventional instruments like spectral instrument. And I would love to try my tomato samples in the Cytoflex with a mixing and autofluorescent extraction. I would love to actually compare and see how good it is compared to Aurora. Is better? Is it worse? It would be good to know. And it's possible. I mean, it's possible to do it. Yeah, I have done it with the CD4 data. So the CD4 data, I did it also spectrally. Yeah, and you get some interesting results in terms of spreading when you do autofluorescent extraction and stain index overall. But yeah, you can do it in conventional instrument as well. But it's just you have less data to play with.
Yeah, so I have a question regarding that I want to come back to. But first, this is a question that I hear all the time in regards to unmixing of heterogeneous populations, right? So you mentioned you wouldn't, so if you apply, let's say non-lymphocytes, if you're looking at what population would you use to extract for unstained to extract autofluorescence? If you're looking at PBMCs, for example, would you gate the entire lymphocyte or leukocyte populations, include lymphocytes and the granulocytes as an average for the extraction, or would you gate individually? How would you handle this?
Yeah, look, it depends. It depends on the population that I'm trying to target, but I would not do a big gates, because this is essentially like mixing 2 fluorochromes at once and pretending that you will get an average. I mean, if it works for you, you can. I mean, it's just a matter of trying. I will typically go for a gate that will capture the population that I'm trying to extract that autofluorescent from. Yeah. So if it's lymphocytes, I think lymphocytes and monocytes are very similar. So maybe you do a gate that have both and you can get something out of it. But typically I would go for a specific population. I don't actually do, unless you're dealing with fixed cells, in which the autofluorescent is similar across the whole lymphocyte range or something, and you can use a single gate and use the default autofluorescent extraction that you have in the Aurora, the tick the box, and mix with autofluorescent extraction that you have. I would typically, for the case of the tomato project, I went for subset specific autofluorescent extraction. So I isolated the autofluorescent of each of the subsets, and then you will try one at a time. So you could try more than one, but there are similarities between the spectra. So if you add them together, you will get essentially errors between them and across all the dyes. So I will do it one at a time. Some people recommend to imagine you create separate, you take the data and you duplicate the data in the Aurora, and each one will have a different unstained control. And your unstained control will be gating around the population that you want to mix and extract the autofluorescent from. You can do that. And essentially you get several sets of data of many populations you have extracted autofluorescent from. But yeah, it's complicated. If you have many populations to deal with, it's a lot of work. It's a lot of work. And I don't think average will work.
Agreed. One of the questions I had, and maybe I missed it in your presentation, it looked like you presented the Cytoflex was more sensitive than the Aurora. So my question is, did you take into take into account the size of the bandpass? Essentially, the bandpasses are bigger, letting more photons in versus on the Cytoflex versus the Aurora, right?
Yeah, look, I get that question a lot. And I can tell you the following. The bandpasses are different. The laser power might be different. The photon density of the laser at the focal point might be different. The flat top might have different geometry. It doesn't matter. I'm not trying to say that if Aurora was like the Cytoflex, they would have the same sensitivity. I'm saying that these two instruments, as they are designed, have different sensitivity. And the sensitivity of the Flex goes beyond the bandpass width. So even if you compare detectors that have similar bandpass, like the APC, for instance, like 660-20 or something, you will get better sensitivity in Cytoflex than imagining a Forte Sound Aurora, which is nothing against any other instrument. It's just the fact that the instrument was designed to be better. So cytometries are typically built around the idea of leukocyte and immunophenotyping. If you want to build an instrument for bacteria and viruses, well, you need to change the way you design instruments. And there are many places in the design of an instrument which you can improve the collection, which is not only the bandpass, and it's not only the laser power, it's a combination of everything. Including, for instance, the design of the flow cell, which I think in the case of the Flex, that's what makes the difference. The flow cell is different. Yeah. But yeah, it's better than any other instrument. It's not weird. It's just the way it is. It's a unique instrument. Not really. It's I have compared it with so many instruments, and it's really better. Which doesn't mean, which doesn't mean, okay, this is a thing that comes out of the equation that I show. Being more sensitive doesn't mean that you will have different results when you're dealing with things like monocytes and macrophages. Yeah. Sensitivity only shows when you're dealing with very rare dim signals in populations of low autofluorescent. If you're dealing with high autofluorescent, sensitivity doesn't matter. Yeah. But if you're dealing with things like bacteria, lymphocytes, and things, you might see the difference. Yeah.
Sounds good. Yeah. So just a question for the panelists. Thinking of autofluorescence, or regarding the nomenclature of autofluorescence, can anybody speak to, does it include non-specific binding of the dyes or cells? That was one of the questions that came in.
What is the question?
So regarding nomenclature, does autofluorescence include non-specific binding of the dye to the cells?
No.
Right. So.
Well, look, autofluorescent will be exclusively the fluorescent that the cell intrinsically produced, which is actually a mix of many different fluorescent molecules, but tend to be typically for a specific subset as given spectra and signature. Yeah, you can call it autofluorescing of monocytes if there is no huge variation. Fixation and any other thing will be adding signal to the cell, but it's an intrinsic matter. You can call it autofluorescent, but it is not typical. It's not essentially autofluorescent. It's just essentially fluorescent added to the cells in the unstained population. But the funny thing is that it doesn't actually matter what the source is. It could be autofluorescent intrinsic. It could be added by fixation. It could be dyes that you have not titrated properly. It could be, for instance, phagocytosis dyes binding to the membrane instead of the vesicles or whatever. You get the same effect. Yeah. It's all the same family, including spillover. Yeah. Spillover is the same. You are adding photons to the detector in which you're trying to measure something else. If you don't compensate, you will get the same issue with this 10 index and resolution.
Yeah. So one of the questions that came in, do you have any suggestions for like when you digest solid tissues that may have a lot of dead cells and how to deal with the high autofluorescence there? Just run them as background, as the unstained control would be a suggestion.
Is it for me? Well,
Yeah, anybody.
no, yeah. Guys, you have to remove dead cells. No, that's a general thing. You have to remove it somehow. The only fear that I have is the especially for instruments like the Aurora, is the fact that you have dyes that you might use because they are cool and they are bright and they are good, but they also bind in live cells. Yeah. My suggestion for anyone trying live dead dyes is to titrate these dyes. Don't just add it, or just don't follow what the company tells you is a recommended dilution. No. Try it. Dilute it until you get what you want, but you don't increase the autofluorescence of the remaining cells. But you need to remove the dead cells because they are a massive source of noise anyway. No?
No, it's good. I do have a comment to both Jolene and Lisa. I personally really want to thank you for showing spectral graphs of your dyes. Do you guys have online tools that you can look at the full spectrum for each of your dyes, or rather than just the peak emission off of one laser?
So I'll answer that for Thermo Fisher. Is we're working on it. Many of our new dyes, we do show some spectra. And I do have to admit that our marketing team is a little behind because our development team has been going full bore. So yes, we do have a lot of that information and it's coming on the website. Going back to all of our dyes, I don't know how much of that will be showing or, going back to reanalyze, so to speak. But for, fluorophores, it's going to be very important to understand what that is. One of the challenges is, of course, this is instrument and configuration specific. So while one instrument and configuration can give you a good idea, it may look a little different in the one that you have. And so that is, kind of a limitation or just a caveat to understand.
So for us, I showed you normalized spectra. So it's normalized to the peak. You can see all of our dyes on that spectra analyzer. And for the new dyes, each of the spark and fire groupings, each of those landing pages, you can see the full spectrum off of a 5-laser Aurora for each dye.
Was that off the SciTech website or your own website?
Ours, we generated it and put it up there. Yeah. So for those specific fire, spark, and the Caravia Blue 520 as well. As Jolene said, to go back through and do all of things like, PE and APC, I think you guys can find those probably through SciTech. But for any of the new unique ones, we are showing the full spectrum off of the 5-laser Aurora for each one.
I can tell you from a fairly early adopter of the technology, it was a struggle for us to build panels at first, right? We didn't have these online tools. So we often ordered dyes from different vendors with different names. And it turned out to be, I hesitate to say the same dye, but the R value was really high. The correlation was 99 or 1. And so there we didn't have a tool at that time to figure out, okay, these two dyes won't work, right? So it's good. And it's difficult for us as users when everybody's renaming their dyes and we can't find the full spectrum up there and compare them one to the next. So from a vendor standpoint, do you think it would be a great tool to have somewhere online from a vendor agnostic overlap with various instruments like the Aurora and the Bigfoot and, you know, the other spectrals that are coming out, that we can select our machines and then select the dies from the various vendors, so we can build more educated panels.
Mhm.
Right?
Yeah, I think it would have to come from a completely agnostic group though, right? So
Right.
to be able to have all the different instrumentation, realistically run all the dies from different vendors on each instrument, and then be able to put the spectra, because you know, you would really need that raw data from each instrument to be reflective, right? So
and I can tell you, even from designing panels for conventional cytometer, I still first go to a spectral viewer, because what a lot of conventional spectral viewers don't show you is the cross laser excitation, which you have to really take into account with all these dies. Almost every die has cross laser excitation, right?
Mhm.
And that comes really helpful. So I think we're at time. Thank you very much for each of you for a great discussion and great talks. And with this, I will turn it back over to Tina.
Great.
Cheers.
Yes, great. Thank you, everyone. Thank you, Ben, for hosting a great discussion, and thank you to our presenters for the morning session. We appreciate your time. Okay,